Welcome, everyone. I appreciate you guys logging in to this webinar presentation of UHPC, and I hope it enlightens you about UHPC and all its uses. A little bit of background, John and Dr. Tadros and I all went to Malaysia with a PCI group in 2016 to see the great work done by Dr. Vu with UHPC, producing structural pre-stressed members in Malaysia. And we came home and wanted to build some mixed designs and design some structural product Tampa plant. And this presentation is basically a review of that relationship and everything we did, in the last 4 years. Anyway, I think it's going to be really exciting. I appreciate you guys taking the time to join us.
All right, thank you, Mace. First of all, I wanted to introduce ourselves. My name is John Lawler. I'm from WJE. I'll be talking first about the material aspects of UHPC and the work that WJE has done with standard concrete products, developing and testing their UHPC mixture. The second half of the presentation will be given by Maher Tadros of eConstruct. Maher is the principal investigator of the research project for PCI that we'll be talking about. I'm the co-PI, but he is the principal investigator. And he'll be talking about some of the findings of that work, talking about structural design and applications with UHPC. So PCI UHPC describes a class of UHPC that has been defined through the research project, the UHPC research project funded by PCI. So our goal with this presentation is to help you learn about some of the key performance characteristics of what we're calling PCI UHPC, and then the applicable design criteria for that material. And also we wanted to talk about potential applications of UHPC and to help encourage everyone's thinking about how UHPC may be best used to address the structural design and construction challenges that we face. All right, so the outline shown on the screen here. We'll start by just talking about UHPC and a little bit about the PCI UHPC project. Then we'll talk about standard concrete products' role in the project and the UHPC they've developed. And then we'll finish up, as I said, with a discussion on the design and future possibilities in the use of PCI UHPC. So to start at the beginning, what is ultra high performance concrete? Well, it's a fiber reinforced material with a water cementitious ratio less than about 0.20. So most of the materials that are used in UHPC are the same as conventional concretes. It starts with the cement and generally includes some amount of supplemental materials, typically silica fume. We add to that a fine sand, and perhaps most importantly, fibers tailored to this specific application. Certainly superplasticizer is a big part of UHPC. That's in order to get the really low water cementitious ratios I was just talking about. And then finally, just a little bit of water to make the material flow. So the biggest difference that you'll notice here relative to conventional concrete is there's no coarse aggregates, at least in most UHPCs. And that's because the coarse aggregates can interfere with the function of the fibers and compromise the overall strength of the material. So how does UHPC behave? Well, there's really three things. First, it has an ultra high compressive strength. It also has very high tensile strengths, and that's both pre and post cracking. And then thirdly, it has enhanced durability due to the high density and the discontinuous pore structure in the material. So of these, the two that really separate UHPC from more conventional concretes are the tensile performance and the great durability. And those are the things I'm going to focus on in the next couple slides. So first of all, UHPC is stronger in tension. I've said that. So tension performance can be evaluated in terms of flexural testing, and that's the basis for the curve that I'm showing here on the screen. So UHPC is stronger in tension to the point that the tensile capacity can actually be reliably used in terms of design of structures. And that's one of the things, again, that really separates UHPC and is the main focus for the materials development. So the material actually carries load after it develops its first crack because the high strength fibers help to carry some of those tensile forces across the cracks. So even after it cracks, the fibers hold the material together and the material absorbs energy as it continues to deform. So going back to the plot, which shows flexural load versus deflection, the blue curve represents flexural response of UHPC, and the area under that curve represents the amount of energy that the UHPC absorbs during that process. And you can compare that against conventional concrete, which is the red triangle. Basically, we have no ductility after cracking. So I also mentioned that the material had superior durability. Obviously in the Southeast, chloride-related corrosion is a prime concern. And so to talk about chloride-related corrosion, I wanted to show you some data from the Corps of Engineers exposure site at Treat Island, Maine. This is an area where there's extreme exposure to marine environment. The tides there are as high as 6 meters, and they get as many as 100 freeze-thaw cycles a year. So there are a number of samples that were put out onto the site for up to 13 years and exposed to those conditions. So the red arrow that I'm showing in the picture there points to some of the samples that have been put out there. And so the samples included the 2 mixes that are identified on the slide. First, a high performance concrete, an HPC, with a water cementitious ratio of about 0.33, 8% silica fume. So certainly not a slouch in terms of a high performance concrete. And then the other samples included ultra high performance concrete with a much lower water cement ratio. So this plot shows a comparison of the chloride profiles measured in those samples. So the plot shows chloride concentration versus depth. And what you can see is for the high performance concrete, chloride was able to penetrate to measurable amounts to depths of around 20 millimeters. In the UHPC samples, the chloride hasn't really penetrated much beyond about 5 or 6 millimeters. So this is pretty strong evidence of how resistant the material is to the penetration of chlorides. All right, on the next slide here, I'm showing a table, again, comparing UHPC properties to conventional concrete. This UHPC that I'm talking about is the UHPC that we've developed and tested at standard. So first of all, we talked about compressive strength being higher. It's generally 3 to 5 times higher compared to conventional concrete. The flexural performance is important here. Reinforcing steel can be reduced or eliminated if that material can really carry those tensile forces. And the UHPC from standard concrete is generally shown flexural strengths sometimes as high as 3,000 PSI after that first crack, which again far exceeds what we can do with conventional concrete. Next topic I want to talk about is shrinkage. Taking a step back, a primary contributor to cracking in concrete structures is restrained shrinkage. That is the tendency for concrete to get smaller as the mixed water evaporates or there's chemical consumption of that mixed water due to hydration. So one of the side effects, as folks might expect, to eliminating the aggregate and reducing the water cement ratio is a greater tendency for shrinkage to develop. But on the plus side here, at least as far as UHPC is concerned, most of the shrinkage in UHPC occurs at early ages. So in some settings, especially in precast concrete, the shrinkage is not that big a deal because it can be more easily accounted for before the structural element actually goes into place. All right, and the last topic I wanted to call your attention to again is the chloride resistance. The 2 properties I'm talking about here quantify how easily chloride ions penetrate into the concrete. For UHPC, chloride penetration measured by the RCP test, that's the ASTM C1202 test, is essentially negligible, less than 100 coulombs. The diffusion coefficient is often nearly 2 orders of magnitude less than conventional concrete, meaning it's somewhere between 50 and 100 times more difficult for chlorides to penetrate through the concrete and cause corrosion of the reinforcing steel. So these together show this property that allows UHPC to achieve significantly greater service life than might be expected of conventional concretes. So talking about more than 100 years, more than 200 years might even be very realistic for UHPC elements. So where does this performance come from? Well, first, it's the fibers. They bridge the cracks and provide the ductility even when the matrix starts to crack. Second, the low water cementitious ratio. It's well known that as we have less water in our concrete, the more dense the matrix can be. So here's a plot pulled out of basic concrete textbook, essentially saying the less water you got, the stronger your material is going to be. Third, the supplemental materials included in the mix, especially the silica fume, bring useful properties to the mix, and perhaps most importantly, they allow for the fourth item, which is particle packing. So what we're trying to do with UHPCs is optimize the particle distributions to get as dense a material as possible. So smaller particles fitting inside larger particles, basically leaving the smallest amount of void space as possible in the matrix, and that contributes to the strength of the material and the durability of the material. But it also contributes, and this may be a little bit unexpected, but it also contributes to the workability of the material, because there's just less space within the material where water can exist, and that's what provides the fluidity to the material. So for all of the mixed development efforts, this optimized particle packing was front and center in what we were doing. So as I said, the slide a few slides ago was based on Standard Concrete's UHPC. Standard was one of the first precasters in the US to develop their own UHPC mix based on locally sourced material. There are certainly proprietary pre-bagged UHPCs on the market that give excellent performance, but they can be expensive. So standards work to use local materials, and this, as I mentioned earlier, is something that WJ helped guide. Their work was really focused on reducing the cost of the mix by taking advantage of local materials. So this slide lists the constituent materials for their mix, and it includes their standard production cement, which fortunately has proven quite conducive to UHPC. That was combined with silica fume, which they had experience using in their Tampa plant to produce a product that saw marine exposure. It included a number of admixtures. They also used a mason sand. This was finer than their typical production sand, but was still locally available. And then finally, the steel fibers. So these materials have been combined in a way that optimizes the packing of particles, as I've been talking about. Right, so due in part to Standard's initial leadership in this area, E-Construct and WJ working with Standard and some other precasters proposed to perform research on behalf of PCI. And so PCI sponsored a project with the goal of developing information that would help the implementation of UHPC in the United States. So the title of the project is Implementation of UHPC and Longspan Precast Pretensioned Elements for Concrete Buildings and Bridges. Excuse me, as the title implies, the goal of the project is to create information for precasters to support the production and structural design of big members. So we're talking about things like bridge girders as long as 250 foot in span, and building floors 60 by 60 foot in size. So there are really two components of this project. There's a materials component and a structural component. On the material side, the intent is to provide guidance on how to design and produce cost-effective UHPC mixtures based on the locally sourced materials. As part of this, we evaluated mixes for 6 different participating precasters, all of which follow that idea of using local materials and largely existing production facilities. Standard Concrete's Tampa plant was one of those plants. On the structural side, the goal is to provide guidance to designers that is straightforward to use and supported by worked out examples. So in terms of the status of the project, phase 1 of the project was completed in February of this year. It started with developing and or characterizing the performance of UHPC mixtures for the different participating precasters. And in general, all the precasters demonstrated that they could produce UHPC based on this process. At the end of phase 1, we generated a report that included a materials guide and specification, but also very importantly, it included a draft of the design guide covering the relevant aspects of structural design and laying out really the plans for phase 2, which is where a lot of the action is that's ongoing right now. So phase 2 is targeted to be completed in April 2021. This included structural testing of UHPC elements produced to evaluate the performance in terms of flexure, shear, interface shear, and ledges. And as a part of the production of samples that were used for that testing, we did a little bit of additional material characterization and are refining the materials documents based on lessons learned during this experience. But finally, the goal will be to refine that design guide based on the results of that testing, and then that will be published in a final form ready to be implemented. So at the beginning of the presentation, I mentioned that we've kind of coined this term PCI UHPC. And the key in our minds here is that this is a type of UHPC optimized for precast, pre-stressed concrete. And by optimized, I mean that we have placed the focus on the performance attributes that are most important for this type of application. So the requirements include, kind of fall into 3 categories. The first is some fresh properties regarding flow and temperature. The second is the compressive strength. We're targeting a compressive strength of 18 KSI. And while compressive strength is relatively easy to test and familiar to most of us, we are de-emphasizing the importance of compressive strength in favor of the flexural strength. Flexural strength is the most important parameter since that's what really adds to the capability of the precast UHPC compared to what we're used to. So in terms of flexural strength, we're talking about a first peak and ultimate peak strength of 1,500 and 2,000 PSI. And then we also have a requirement that the peak is at least 125% of the first peak. This is to ensure that the material has a strain hardening behavior and has that nice post-peak ductility that I showed on the plot in one of my earlier slides. So as discussed, Standard's Tampa plant has played an important part, in the PCI project. And this has included production of some of the structural test specimens that I was alluding to in the previous slide. So doing producing UHPC at Standard required some careful attention to their materials handling, batching sequence, concrete placement, finishing methods, as well as their QC testing procedures to update things relative to what they usually do with conventional concrete. But they've worked through these challenges very well and have about a half dozen UHPC pours under their belt to date. So as part of the PCI project, Standard has produced 2 long span test pieces, a box beam that was actually part of phase 1, so that happened back in 2019, and then a decked I-beam, which has been part of phase 2, that has just happened this summer. I guess it's also worth mentioning that they've done a few additional types of pours. They've produced some hollow octagonal piles, as well as some other work for FDOT. All right, so in the next few slides, I'm going to show you some images of production at Standard to give you a feel of kind of what they've done. These pictures show a hollow box beam section set up for UHPC. So that's the picture on the left, and you can see in the middle there on the top, the cross section with the void in the center and the limited reinforcing steel. Contrast that to the picture on the right, which is a similar element, but as would be produced with conventional concrete. So that's obviously going to be cast solid with much more reinforcing steel. And so with the UHPC, the intent here is that we're going to be able to rely on the tensile capacity produced by the fiber reinforcing in lieu of all that reinforcing. All right, so I'd like to show you a quick video of placement of that box beam. So this illustrates the flowability of this material. You can see it kind of traveling along the top of the foam void former. You can see it flowing around down the sides, and it's a little hard to see, but in the bottom of that hole there, there is UHPC that's actually flown down around the sides and along the underside. So the full placement of this nearly 50-foot beam took about 20 minutes to accomplish. All right, so this is what it looked like when it was finished before they covered it up for curing. You may be aware that some UHPC is steam treated after curing to encourage hydration of the silica fume and the other cementitious materials. But in fact, you know, the warm ambient temperatures in Florida can also aid the hydration process without the need for external heat. So the internal temperatures in this particular product reached about 180 degrees just with that ambient heating. A lot of that had to do with the heat of hydration with the high cement contents, et cetera, in the mix. And that heat, however we get it, contributes to the ultimate compressive and flexural strength of the material. You may be thinking temperatures 180 degrees or more might start to become an issue with DEF, obviously concern with conventional precast concrete. But generally DEF is not a concern in UHPC because of the low moisture permeability in the material. Water just can't get in it to support that reaction. And the silica fume is also generally used in high dosages, and that's beneficial as well. All right, so here are some images of the finished product after it had cured out. On the left is a photo actually of the underside of the UHPC. You can see the self-consolidating nature of the material contributed to complete flow underneath the blockout. And in the middle on the right, you can see side-by-side comparisons of the UHPC and the conventional concrete. The UHPC is the darker beams, I guess, on the right side of both the photographs. All right, so during all of this production, the material's properties were carefully monitored. Tests of the compressor strength were done based on lab curing and on match curing, where we see the benefits of the internal heat of hydration on the compressive strength. So these are the results compared against the 18,000 PSI target. Certainly we have far exceeded those. The flexural strength and ductility also well exceeded the targets with the ultimate flexural strength of over 3,000 PSI relative to our target of about 2,000. And certainly our peak as a percentage of the first peak also far exceeded our target of 125%. So I just want to reiterate that these properties were based on the mixture developed for standard that relies on local materials and existing equipment to control the costs of this UHPC. So from a materials perspective, the goal here has been to produce concrete products that bring value through efficient design. You know, with this material, we can use things like voids in the middle to reduce weight by up to as much as 50%, and then also bring great durability and the long-term life cycle cost benefits associated with that. So with that, I'll pass it over to Maher to talk about the structural design approaches that take appropriate advantage of the excellent properties of UHPC.
Thank you, John, and thank you, Mace. And thank you everybody else for attending today. The outline of the presentation is going to cover flexor, shear, interface shear, optimization of bridge superstructures, deck I-beam, composite deck I-beam, box beam, and some recent activities. This is a repeat of what John has said. The emphasis here is that the PCI UHPC is a material that has very specific requirements for structural design. And any precaster who produces it and meets these requirements, then he meets the qualification for PCI UHPC. The primary requirement is flexural tension, cracking stress 1.5 KSI, ultimate stress 2 KSI, and then you have strain hardening that allows the cracking stress to continue to go up with the load, that allows the stress to continue to go up with the load up to the peak value, and the peak value has to be at least 125% of the cracking stress. And then the ductility requirement. So the most important property for us in structural engineering is to make sure that we have the tensile properties that we need, because when we do our structural optimization, we're going to take advantage of that. Fortunately, standard concrete products started earlier than anybody else, but there are several other precasters, about 8 or 10, that have joined since that time. And it appears that just about everybody is on their way. You could tell from the chart on the left that we don't have any shortage of meeting these minimum requirements. The chart on the left gives you 2 dashed lines. The top dashed line is the what you would have to check for to qualify the material, and the dashed line on the bottom is what we use in design. So what we're using in design, we use what's called inverse analysis to convert the information that's coming from flexural testing to a stress strain diagram that we can use for strength calculations. And we are proposing a modest 0.72 KSI. Dr. Graybiel, in his excellent work over the years, many years now, has led the way, and some of his testing showed 1.5 KSI for some of the pre-bagged materials he had used. For us, we want to be conservative, and we know we can achieve more, but we want to be conservative to make sure that we have enough confidence in what we're doing before we move full speed ahead. So this sketch appears to be a little bit complicated. It really is not. All you do is take the strain diagram, convert it to a stress diagram from the previous slide, and calculate stresses, forces, and moments. One extra step we do is we use our standard computer programs with equivalent compression block. And as you can see here, whether we ignore the tension at the bottom due to fibers or not, the results come very close to a more sophisticated nonlinear analysis. So for pre-stressed concrete, we are going to most likely recommend to people that fibers be ignored. They don't have to be. The spreadsheet that we're offering in the project will allow you to include them or ignore them. For non-pre-stressed concrete, for example, the flanges of an I-beam that has wide flange or a box beam, and if you do not have pre-stress in the transverse direction, which usually don't, you have pre-stress only in one direction, then you're counting on the fibers and the rebar. So if you're doing the fibers alone, you would be assessed a resistance factor of only 0.75. If you're doing a combination of fibers and bars, then the resistance factor could go up to the factor with bars alone. Service load is very straightforward, nothing special. All you do is just do service tree analysis using the codes that you have, and in service 1 for compression, and check that the tensile stress is less 1 KSI. Remember, cracking is 1.5. So we're taking a cut of 1/3 of the 1.5, and we're saying, just limit yourself to 1 KSI. That's more conservative than what we do with conventional concrete. Vertical shear, the equation appears to be a little bit intimidating, but it's really exactly what's in the AASHTO specifications, with the exception of one term that's being added. It's called V sub F, a new term. But V sub C, linear strain that you get at mid-height or at the bottom, beta value, are all the same. In our recommendation, we are recommending that you do not limit yourself to cut the strain off at 0, but you can go to a negative strain if you need to, because that gets you the cracking angle to be closer to what we are seeing in the experiments. The bottom line from all of this is that you have a V sub F, which is the new term. That's the only thing that's new. And the V sub F has to do with the stress that comes from the properties of the material. Again, PCI, UHPC material. The cotangent theta that comes from the equations, and dV, dV. And our testing, as I will show you here later, is it's extremely conservative to use 0.75 KSI. In phase 2, we may decide to stick with that or raise it a little bit to remove the extra conservatism. So we went ahead in phase 2 and decided to test what we issued as a preliminary design guide. And we tested a whole lot of specimens with very different variables. And this picture shows the types we've used. At the top, we have forms made by Hamilton form for these beam shapes. They go from 2 foot 10 inches to 4 foot 6 inches in height. So they are reasonably good sized beams, but these were all shear specimens, component testing. We also tested a decked I-beam. We call it a decked I-beam, the one on the bottom left. And that is for a company in Canada that's part of the program on a bridge we designed for them at eConstruct, and they are in the process of building. And then a novel new shape for buildings is called ribbed slab. And finally, the box beams that John talked about. This presentation, this shows you a quick video of typically what happens in all of these beam tests. Lots of cracks, and that's very similar to what Ben Graybiel and his staff have demonstrated over the years, very similar. And very flat angle, 30, 25, 30 degrees. And then suddenly, one of those cracks expands into a major crack and the beam collapses. So let me get out of this one. When we compare the test results with what we have recommended in phase 1 with F sub RR equal to 0.75 KSI, you see that that orange line is much higher than the green line we predict from theory. So we're very, very conservative, very safe. Another way of presenting it is that you see that the test force is on the high side as opposed to the theoretical value is always higher than the 45-degree line. And it tells me that we're conservative in all cases. Maybe there are 2 cases that are close to the line, but there's a story behind these 2 cases. So the majority of the bridge products would have a significant margin of safety. One thing we have to emphasize to you as you go through your design is to make sure that you have enough anchorage of the flexural reinforcement into the end zone. Because if you don't have that anchorage, you don't develop the arching effect and you don't develop the capacities. And that's nothing new here. That's the same thing as we would do with conventional concrete. We have a benefit here, and that is reflected in the fact that development length is only 40 bar diameters, 40 strand diameters. So for a 0.6 inch strand times 40 is only, what, 24 inches? For regular concrete, it's 150 strand diameters, huge difference. So This concrete binds onto the strand much, much better than conventional concrete. That helps develop the strand in the end much quicker than conventional concrete. Now interface shear. Again, we found through our studies, and as I said before, and I'm repeating, we're not in the business of discovering new theories. In the PCI project, we just want to know what exists, try to assemble it in a form that designers can use, and try to see what gaps exist and do additional testing to assure ourselves that what we're recommending is very safe and very conservative. We borrowed an idea from abroad, and mostly the French people, but also the Asians and others are recommending that we use what they call fluted or corrugated shape on the top of the precast UHPC beam. And that can be formed with form liners, and 3 of the precasters tried that successfully, using form liners to create the deformations on the top flange. The equation that we are proposing to use is the same standard form that we have been using for years for ASHTO. A cohesion factor times A plus a friction factor times area of steel times Fy. Except in this case, really, there's no cohesion. That concrete is impervious. There's no paste that can go and penetrate through and create that cohesion. It's like glass. Methods of connection, typically in bridge applications, we would have a PCI HPC beam made composite with cast in place deck. It's not what I would recommend, but that's what a lot of people would want to do. In the Midwest, where you have snowstorms and de-icing chemicals, you need the UHPC in the deck more than anything else. But as a starting point, you can do a UHPC beam with a conventional concrete deck. The best solution is to form the corrugations, as I indicated before. And so mechanical interlock is the most important item there, and we still need to put some rebar to keep the pieces together from separating. An interesting exercise is what we're doing at Standard Concrete Products, and thanks to SCP for that. We had them make a type 2 beam, ultra high performance. We didn't introduce the web. And we had them also make precast deck panels separately. And we connected them in the plant before they got shipped. I believe they have already been shipped to the Florida DOT structures there for testing. With this experiment, we're able to adjust the elevation of the deck any way we want to. If we want to have a cross slope, we can have that. If we want to have a certain camber amount or flatness or whatever, we can have that in the haunch, in the gap that exists between them. And the types of connections are just a threaded rod on the left third of the beam, just a pocket on the right 1/3 of the beam, or both of them, a pocket with a threaded rod in it, and the pocket is filled with ultra high performance concrete. Testing is expected to be done in the next several weeks. So this shows pictures of production of the I-beam and the panels. And this shows a picture of the assembly of the deck panels with the I-beam. One cross-section that appears to be optimum in structural design, but also difficult in forming, is to take the idea that FHWA helped Iowa State University a few years ago with, which is called waffle slab, and combine it with the I-beam itself to create what's called decked I-beam. If you do that, you're really doing the most optimum design of the member and also helping with accelerated bridge construction, which is a good buzzword these days, because you already have the deck part of the precast beam. So that was the beam that was made by FACA in Ontario, shipped to NC State University, and tested in flexure shear. And we didn't want to damage it in flexure, so we tested a little bit above the factored load. We knew that it was surviving. In fact, you could not see any cracks. You could only detect cracks with electronic equipment. And now this is the important picture here. You can tell that there's plenty of capacity in this member in taking the factored load without even becoming nonlinear. That's the shear test. So you have a lot, even if you predict theoretical capacity, and with a high F's of RR value, you're still below the actual test value that came. The other side of the beam was also tested, and it was a bust. It was a bust. But you learn a lot of good lessons for something that has not worked well. And the planning for this was to have the end fail in shear, but would have stirrups in it. The precaster, unfortunately at that time, but fortunately now, did not put enough flexural reinforcement to force the failure to be shear failure. So we started to have cracking, and you will notice here these vertical lines. Cracks are at every single bar, every single stirrup, which are number 5 at 10 inches. And then eventually the beam failed in flexure. It did carry enough shear higher than the theoretical capacity, but it would have carried more. Having bars in there would help you get more shear capacity. But what for? Why would you want to do that? If you put rebar in the web, you're actually obstructing the flow of the fibers. You're gaining capacity that you don't need. So I strongly recommend that you don't use bars in the webs. Now, ideas for future development, just so ideas that were not part of our project, but I think are important for people to try to pursue, trying to motivate others in the audience to help out with some developmental work. This is a deck panel that is made out of, now this is just the form. What you see is just the form. Ultra high performance concrete, full width of the bridge. This was just a specimen, so the bridge only 12 foot long, but you would have panel full width of the bridge, reinforced with a wire truss, and the thickness of the panel is only 1.5 inches. And the intent here is to use this to support the overhangs, which are a pain in the neck when you do cast in place deck. But more importantly, it's impervious. So if you're in Florida and you have low bridges and you're shooting that salt water into the bottom of the bridge that eats it up, you'd have that layer of ultra high performance concrete that protects the underside of the bridge. It ends up being topped with cast in place concrete topping. So we had that, and we tested the very few specimens, a couple of specimens, and they seem to work very well. So that's an area that's worth pursuing with a more detailed research program. Another item is the box slabs, and I believe this is ready to go. Box beams are not difficult to form. You can get expanded polystyrene void forms to create the void, and you can take advantage of all the benefits. You can go from 1 foot 6 inch deep to 8 foot 3 inches, from 50 foot span all the way to 250 foot span. And it's very simple to do, almost no rebar in it. And this is a project that we are doing at this time with Florida DOT to try to propose an alternative to a cast-in-place slab bridge being built in the Panhandle, or about to be built in the Panhandle. So we're replacing the 1 foot 5 inch slab with the same depth, voided box, pre-stressed, with only rebar to create the connections between the box beams. You can have U-beams. Again, that's kind of down the road in the future. If you are interested in that, this is a hot item in Malaysia. They use it quite a bit. Another product that we're lucky to have Standard Concrete product help us with is to create an octagonal box from the square 24-inch box. The volume of concrete is about a half. You only need the strands. You don't need a spiral. The spiral at the end may or may not be needed. We put a spiral at the end, but we don't know if it's needed because we never drove this pile. And we took it to FDOT and tested it, and it performed extremely well. That's one type, and I realized that there are some other people that are working with edge piles, but piling and also sheet piling are hot items that I think need to get our attention. This is the standard sheet pile from Florida DOT. The thickness is 10 to 12 inches. And we found out from the Europeans in the Netherlands, they can create UHPC with a thickness of only 4 inches. So there is potential here. The question is, when can we start designing with UHPC? And the answer is now. Not in 2 years, not when phase 2 report comes out, not when Dr. Graybill and all of the wonderful researchers around the country do the research. That will never end. We already have enough information to design and build bridges, and we have. The information and the knowledge continues to improve, but that should not stop us from trying. So, in my opinion, recipe for success, start with something simple. Get as many spans as you can on your project to try to get into the steady state and optimization process. Start with relatively short 60 to 80 foot span. Preferably, you can justify your work if you are in an aggressive environment. But even in non-aggressive environment, it still comes out fairly cost effective. Simple cross section, the box slab is wonderful. Aim for 50% reduction in the concrete volume, and for just about 80% or more of the rebar. And be conservative. Don't go to the edge, because you can still have a cost-effective design without having to go all the way to the edge. This is my presentation. Thank you very much.
All right, thank you, everybody. Thank you, Maher. So we have opened the chat for everybody. If anybody's got questions, please go ahead and submit them. I guess there is one question that has come up and usually does come up related to UHPC. And I guess that is, can we talk a little bit more about the cost benefit analysis of UHPC at Standard Concrete? And actually, I think Mace is probably best able to answer that question. Mace, do you want to unmute yourself and respond?
Yeah, great. Now so I mean, this is a question that comes up all the time. I think what we're seeing is that using our locally sourced materials to produce a UHPC mix, we're at about, with materials and the cost to produce it in the plant, it's about $1,000 a cubic yard, the cost of adding the fiber and the labor associated with the time of the mix, versus, which is about a third of the cost of like proprietary mixes like ductile and other stuff. It's so I think that makes it, it's obviously significantly less than a proprietary mix. And then what I'm seeing is that when we start comparing UHPC to other like corrosion resistant materials like stainless and carbon fiber, UHPC, it's very competitive and introduces, so many more additional benefits by having like a more efficient structure, and the concrete durability is so much greater. And these, so when you're in a corrosive environment and you want to use stainless, having a durable mix like UHPC is a significant benefit. So, and what we're, by reducing the weight of the materials, when you're designing with UHPC and we're cutting out almost 50% of the weight of a concrete product, you're adding, the cost benefit analysis, it helps so much with UHP. Even with the more expensive concrete, you can be more efficient. I don't know. I think that answers it. Thank you, John.
All right. Does anyone else have questions for the presentation here, for myself or for Maher?
It looks like, yeah, the cost per cubic yard, I see that. And then Richard, I think he had a question about what is the biggest advantage, strength, compressive strength or tensile strength? I think just reviewing that issue.
Maher, do you want to speak to that?
Well, the biggest advantage, the obviously easy test to do is compressive strength. That's what we all migrate to. And it's a good measure of the quality of the product. But we really hardly use that 18,000 PSI in any of the products. We could use it in a very extreme case when you have a very long span with a short depth and all that, but that's not what people should be doing. It's the tensile strength that allows us to eliminate a lot of the rebar and get the webs to be 3 or 4 inches wide. That's the most important item.
All right. Well, if anybody else has questions that come up after the discussion here, please reach out to Mace, myself, or Maher. I'm sure we'd all be happy to respond. So I guess with that, we'll wrap up. So to conclude, thanks very much for your participation. All of us at Standard, eConstruct, and WJ are certainly excited about the possibilities of UHPC. As May said, starting back in Malaysia, through all the work that we've done through the PCI research project, certainly see lots of potential with UHPC, and we hope that many of those of you that are listening here will be a part of the future use of the material. And with that, I'll turn it back over to Maher. If you want to make a final closing comment for us, I'd appreciate it.
Well, what I could say is that this has to be one of the most exciting developments in recent years. And it's a structural engineering challenge. And we structural engineers tend to be conservative and don't want to do anything that hasn't been done before. So I would strongly encourage fellow structural engineers to get out of that mindset and try this wonderful material. And once you try it, you're going to fall in love. You'll get addicted. Thank you. John?
Yep, I think we're all set. Thank you, everybody. Take care. Enjoy the rest of your day.